Section 21.11. The inner sphere mechanism. The inner sphere mechanism involves more steps than the outer sphere mechanism. So we can look at the inner sphere mechanism here on the left. These two complexes get close to each other. There's a bond breaking between these two. The orange sphere has left the transmetal center, and now this blue sphere can serve as the bridge between these two centers. Electron transfers from one transmetal to the other through the bridge. And then we have this bond breaking here. This transition metal and this blue sphere breaks from each other, and then the orange sphere get back to the other transition metal center. So in this inner sphere mechanism, very likely you observe the ligand exchange. All right, this blue was bonded to here, this orange was bonded to here, but now they are exchanged. And also the electron transfer goes through the bridge. And now you can see there are just many steps in this inner sphere mechanism. Outer sphere mechanism. These two get close to each other, and as long as that they are close enough, electron transfers from one transition metal center to another. Okay, from here to here, there's no bond breaking, there's no bond formation. It's just the electron transfers from one transition metal center to another, as long as they are close enough. Now let's focus on the inner sphere mechanism. What's the rate limiting step of the inner sphere mechanism? Well, the rate limiting step is usually the electron transfer step. And inner sphere mechanism is usually faster than outer sphere mechanism. Why is that? Because the electron transfer can go through the bridge in the middle. So it goes through the bonds. And that's why the energy barrier is usually smaller in this rate limiting step, the electron transfer step in the inner sphere mechanism, especially when you have some conjugation, right? Some kind of conjugation, pi-type conjugation in the bridging ligand. And then the electron flow is easier, the energy barrier is smaller, the electron transfer is faster. So that's actually why the inner sphere reactions are often faster than outer sphere reactions. Okay, in outer sphere reactions, you have to just have two transition metal complexes, and then one electron just jumps from one transition metal to the other. Okay, you need to somehow overcome a large attraction between this electron and the transition metal it comes from. All right, that's why outer sphere reactions are often slower. So now let's get back to the inner sphere mechanism again. Usually the rate limiting step is the electron transfer that goes through the bridge between these two transition metal centers. But if both transition metal ions have a non-label electron configuration, okay, that means really large ligand field stabilization energy, very high oxidation number, something like that, and then when these two transition metal centers are connected by the bridging ligand, it's very hard to break this bridged complex. The breakup of the bridged complex becomes the slowest step, or the rate limiting step in the inner sphere mechanism. All right, so usually the electron transfer is the slowest step, but it's also possible that the breakup of the bridged complex can be rate limiting if both transition metal ions have a non-label electron configuration. For example, very high oxidation number, 4D or 5D transition metal centers, or very large ligand field stabilization energy. For example, D3 in an octahedral environment, D3 has a very large LFSE. Or low spin D6, very large LFSE, right? So experimentally, we can determine whether the electron transfer from one transition metal to another is inner sphere or outer sphere. This is based on the individual steps in these two mechanisms. All right. Over here, the electron transfer is usually the rate limiting step, right? And this electron transfer goes through this bridging ligand. So that's why the structure of this bridging ligand matters to the electron transfer rate. So we can just try different bridging ligands that have different abilities of passing through electrons quickly or slowly, and then if that affects the overall electron transfer rate, and then we can tell it's inner sphere mechanism. Okay, now let's look at the outer sphere mechanism. So if we use different ligands, but the reaction rate constant of the electron transfer is not affected significantly, very likely it's outer sphere mechanism. Because in the outer sphere mechanism, anyway, the electron just flows from one transition metal center to another directly, without going through any ligand, without going through any bridging ligand. So if the structure of the ligands do not matter, well, then very likely it's outer sphere. Okay, now let's try different ligands. Okay, we're going to allow the electron to transfer from ruthenium 2+, okay, over here, with an oxidation number of 2, to cobalt 3+. Okay, the electron will go from here to here through this ligand. So the electron can flow to here and then go through double single over here. Well, there's not much conjugation. I would say just a little bit of conjugation here. Okay, because this can be double bond, this can be single bond minus, right? So a little bit, and it goes through here. If you look at this structure, in this ring, you have nitrogen in the first position, and this substituent, this functional group, on the third position. All right. What's the electron transfer rate? It's 0.016 reciprocal molar reciprocal second. Okay. Now, when we change the position of this functional group to the para position, to the 1,4 position, the electron transfer rate becomes 100 reciprocal molar reciprocal second. So if you compare 100 and this 0.016, they differ by a factor of 6,000 just because you move this functional group from position 3, the meta position, to position 4, the para position. All right? And that indicates this electron transfer mechanism is got to be the inner sphere mechanism. The bridging ligand matters a lot. They differ by a factor of 6,000. The para position gives you the much larger electron transfer rate.